Welcome back. Today we shall take up some more examples for aromatic character. Till now we have considered only those aromatic molecules which are even number carbons or which are neutral. Now what we are going to do today is we shall take up those cases which may be containing odd number of carbon atoms or those containing charges, maybe cation or anion. So if the species is charged one, do we have the aromatic character expected in them? Because charged species are normally unstable, difficult to create also. Is it not? That is a general impression one has about the charged species. So what I'm going to do today is I will now take cyclopentadiene. The structure I'm going to write in a minute. No? Try to watch it. Cyclopentadiene. So how does that molecule look like? It's a 5-membered carbon. This is how it looks like. A double bond here, a double bond here. Therefore, this carbon is sp2, this is sp2, this is sp2, and this is sp2. Because it has two hydrogens here, 4 single bond, therefore this is sp3. Straight away, there is no continuous ring current here. There is a break. Therefore, this part is not even part of conjugation. This is non-planar, that is tetrahedral environment. To start with, this ground state or the neutral molecule does not have any symptoms of aromatic character. But suppose in a reaction, I want to give some reaction and then again restate aromatic character again after the reaction has been carried out. So one reaction I want to carry with this molecule is I will be adding to this a strong base like tertiary butoxide. Remember alcohols, if the molecule is ROH, if I convert that to RO minus, this is definitely a strong base because this is a weak acid. The conjugate base obtained from that must be a strong base. So what is the base I am taking here? I am taking tertiary butoxide, which is a very strong base. Now, once I am adding a strong base and I carry out the reaction, I realize this particular molecule is functioning as an acid with a pK value of approximately 16. It's a promising value, 16. What is the minimum meaning of pK at this stage? It indicates the strength of the acid. Just like pH values are normally used to interpret the strength of the acid. How did we interpret the pH value if you remember? Lower the value, it is a stronger acid. As the pH value keeps increasing, the acidic strength will come down. In a similar way, one needs to interpret the pK value here. So this is the pK value for that. I feel this value is promising because one of the hydrocarbons, which all of you must have read, is alkyne triple bond, and that I am referring to terminal alkynes, R, C, triple bond CH, and this is sp carbon. If you correctly understand the hybridization here, there is a inductive effect moving this direction because this is more electronegative, and there is a plus charge to this. So terminal alkynes is the first instance probably, or one of the first instances probably, where you have seen acidic character for a hydrocarbon. Now this is acid. Compared to this particular acid is about 10 power 8 times stronger. This acid. That means this particular molecule, even though it does not contain sp carbon, nor do we have any inductive effect strongly operating there, but still it is able to show appreciable acidic character. Now to account for that, I must realize, to account for this reasonably strong acidic character compared to other hydrocarbon situations here, in that case, this is lost as proton because that is a base. So what am I getting here? I am getting a cyclopentadienyl with a minus charge here because plus is gone. And the minus charge of course is not localized. This is part of delocalization. Therefore, if you watch out, I can continuously write down different resonating structures. Let us write them down now, first point, so that you understand thoroughly both the approaches for resonance theory as well as aromatic character as enunciated by Huckel's theory. Suppose if I am having this molecule with a minus charge, single bond here, That is lone pair, single bond, double bond, single bond, double bond, single bond. 100% conjugated structure. So what should I do now? I will write down all possible resonating structures. I'll get a minus charge here now. If it continues, I am getting a double bond here and a minus charge here. And if it continues, I will get a double bond, minus charge here, and double bond, double bond. Therefore, if I am to write a sort of hybrid structure, this is how the negative charge is delocalized. And negative charge is residing only in the carbon atom. Normally, if you remember, carbon atom it does not have the potential to carry the negative charge. But the interesting thing is, this is part of pi bonds. And how many pi electrons are totally involved here? 6 pi electrons. Therefore, this particular conjugation will definitely lead to stabilization because 6 pi electrons are involved here. And what is the sanctity of the 6 pi electrons here, please? These electrons will completely fill BMOs, bonding molecular orbitals of this particular anion. Whenever they are completely filled, what does it mean? It is a stable arrangement. This is what we observed other day with reference to benzene also. So this molecule is stable. At the same time, what is the point of caution? You should not stretch out and tell, okay, this is like benzene. Benzene is neutral. Remember that point. And benzene is a hexagon with ideal placement of carbon atoms. So therefore, just because it is an aromatic sextet in both the instances, you should not say it is like benzene. The correct comparison is between comparable things, please. Suppose I am writing this molecule. Imagine again I am rewriting the cyclopentadiene with a negative charge. Imagine this is my molecule and I am getting a minus charge. This is my anion. Versus I am writing one more structure. See what I am doing here. I am having a double bond, CH2 minus. So totally I am having same number of carbons in both the cases. This is acyclic. This is unstable. Even though I can show some stabilization here. Some delocalization I can certainly show here, is it not? But this versus this, if I take, this is many times stable than this. That is how you need to compare stability between two comparable species here. So I can definitely stabilize C minus now because it gives you aromatic character for the cyclopentadiene anion. Out of curiosity, I want to know what about this species. Suppose imagine, again I am writing cyclopentadiene with a plus charge over this. Remember, this plus charge means what? This is a vacant orbital. Do you realize this is part of conjugation? The p orbital, single bond, there is again p orbital, there is a p orbital here prior to formation of the single. That means even this is possible. In terms of delocalization, both have equal rights to form. But there lies the importance of Huckel's rule. This species is highly unstable. It is highly unstable, no doubt about that. Because it involves 4 electrons. It is anti-aromatic in nature. Let me give one very good illustration so that you remember this point. If it is coming in examination, you must be able to handle that quite fluently. Suppose imagine I am taking a molecule again cyclopentadiene with a OH group here, an alcohol. Remember, you must have encountered large number of reactions where alcohols in presence of H2SO4 concentrated, they lose water molecule easily. Correct? Therefore, again, to this I am adding here concentrated H2SO4. Constant H2SO4. In that case, what is the expectation normally if you don't consider other things here? The H will come and attack here, and this entire thing is lost as water. This is lost. So, what is the resulting species, please? The resulting species is plus charge. But I want to tell you this reaction is not working. You can't dehydrate the molecule. Therefore, cyclopentadiene does not have the tendency of forming a cation. It has a tendency of forming an anion because the delocalization there leads to stabilization, whereas the delocalization makes it unstable. This is anti-aromatic. Therefore, tendency of cyclopentadiene is to form an anion. Hope that point is clear for you. Next, I want to take now a 7-membered cyclic conjugate cyclic system here. That is, I want to take cycloheptadiene now. 7-membered, odd number. So I am taking here 1, 2, 3, 4, 5, 6, 7. This is 7 membered. Therefore, let's imagine there is a double bond here, single bond, double bond, single bond, double bond. Therefore, this portion again is a gap. It is not totally a continuous ring. The entire molecule is not conjugated, and the planarity is not there because that is sp3. Therefore, now as you can make it out, getting a plus charge and getting a minus charge, two possibilities. Either plus charge or minus charge. Is it not a fact? In either case, we can delocalize the electrons. But again, you must keep in mind Huckel's rule. Suppose imagine if I am getting a plus charge, if I am getting a minus charge here. If I am getting a minus charge means again it is conjugated system. Don't commit that mistake. If I am having a minus charge means one more lone pair. Therefore, totally 8 pi electrons are there. 8 pi electrons. It corresponds to 4 in role. Therefore, that kind of delocalization does not impart stability to the ion here. Therefore, this particular molecule does not form an anion. Anion was feasible and possible for pentadiene molecule. In this case, anion formation is discouraged. We don't get that molecule. Therefore, this molecule has a tendency of forming plus charge. If the plus charge is there, imagine, if the plus charge is created in the course of a reaction, are you watching out? It corresponds to 4n plus 2 pi rule, our Huckel's rule. Therefore, creating plus charge or cycloheptadiene is easy. Again, should not compare with Venice, should not compare with Venice. I can compare with some other acyclic compound carrying 7 carbons with a plus charge. Comparisons are always between comparable things. Therefore, this particular molecule has a tendency of forming cation. Let me give one beautiful illustration by which you can remember this example. Suppose imagine I am now taking, again I am writing the same molecule again. So I am having a double bond, double bond, double bond. Imagine I am having H and OH. I am taking an alcohol. Remember earlier we have taken OH for pentadiene molecule and we saw the reluctance of that molecule to lose OH as water molecule because that is to anti-aromatic foreign rule. In this case, even if I am not using concentrated, I repeat, we require H2SO4 for taking one water molecule. I am not even employing concentrated H2SO4. In fact, I am taking for this reaction dilute H2SO4. That means there is a lot of water there. In that case, that H will go here and this is knocked out as water molecule. And the species I am getting is a plus charge here, double bond, single bond, double. This is the species I am getting here. A tropinium cation is obtained. Probably this is one of the good examples to remember where a carbocation can be isolated in an aqueous medium. Why do I call this aqueous medium? This is predominantly water in which I have added few what's called traces of H2SO4. It is highly diluted condition. In spite of highly diluted condition, we are still able to carry out the dehydration reaction. Recollect, all dehydration reaction that you have read, you have necessarily employed concentrated sulfuric acid, never dilute H2SO4. This is one good instance where a carbocation can be generated and it continues to stay and generate using and it can survive in aqueous medium also. That is the beauty of this example. Such that I have given this example so that you can remember 7-member ring plus charge stable, 5-member ring it is the minus charge that is stable. Both are what's called charge species only. Let me give one more illustration. For example, other day we have seen this molecule cyclooctatetraene. I am redrawing that. Cyclooctatetraene was, of course, I am considering even molecule here. This is what we have originally. This is cyclooctatetraene. This particular molecule, other day we have seen, if the entire molecule is planar, it could have become anti-aromatic. Because it is not planar, we say it is non-aromatic system. Now, this particular molecule can be, in a reaction, can be made to accept 2 electrons. Interesting thing. Suppose if I had 1 electron, I will get 1 minus charge, isn't it? Any charge species to create means the molecule is not stable. In place of that, if I am creating 2 minus charges, it is not normally we encounter. Of course, we have seen instances where O2 minus is existing as oxide routes in the nature. There, because of the lattice energy, there is the stabilizing feature there. In this case, what is the stabilizing feature? Suppose if it is accepted, imagine I am adding two potassium ions, potassium being the first group metal, they give you one electron easily. So from this I am getting two electrons, therefore it is accepting two electrons. That is, I am getting a dianion. Dianion. Interesting case. And now it becomes aromatic. Even though it is having double the minus charge here. This must indicate to us the importance of Huckel's rule, which will make the molecule to go for filled configuration from the BMO section of the entire MO diagram. Therefore, this ion, dianion, can also be formed. I did not talk about the three-membered ring. It is quite easy. You can make it out. That is three-membered. Suppose if I am taking cyclopropene molecule, I am having here. This is again an odd number molecule. There are hydrogen here. There is no question of again same sp3 is a stumbling block as we have encountered in cyclopentadiene, as we have encountered cycloheptadiene. Now in this case, if an appropriate group like chloride can easily be knocked out when you add AgNO3, I am getting a plus charge, it can be stabilized. And the value of N is 0 in the 4n plus 2 category aromatic section. Therefore, there are a good number of instances where a reaction is promoted because the charge species I am getting has become aromatized, and interpret the aromatization clearly without going for comparisons. It's somewhat comparable things when you compare so that you understand what is the meaning of aromatization leading to stability. Therefore, I am having quite a good number of cases where charge species are formed. I wish to take up one more example in the remaining time wherein I want to take 5-membered ring and 7-membered ring combined together as a condensed system. Let me write that molecule. 5-member, because already we discussed 5-member and so we have discussed pentadiene, we have discussed heptadiene. Let me combine them and see something interesting I want to talk about the remaining time. Suppose if I take now a molecule which looks like this. So this is pentadiene section molecule. 1, 2, 3, 4, 5, 6, 7. So I am having a double bond here, double bond here, double bond, double bond, double bond. This molecule is azulene, 5-membered ring and 7-membered ring. Entire thing is conjugated, is it not? So we can see. Suppose if I am to move these electrons here, in that case I get a plus charge here, correct? Therefore, if you watch out, the electrons are moving throughout the ring, and as the electrons move to this side here, this electron density will increase here in the azulene. I wish to show one structure, plus charge here, and this of course rotates. Are you getting that point? Therefore, there are plus charge species, that is, if you take this molecule in the neutral state itself, there is a dipole moment. The direction of dipole moment is towards the 5-membered ring. It is reasonably good value, 1d by value. That means if you write down the resonance hybrid for this azulene molecule with the 1d by moment, permanent dipole in the ground state itself is. So how does this molecule look like in the hybrid structure? Right? I am having a negative charge here and I am having a positive charge here, both with 6 electron space. Very good aromatic system. This is only dipole moment. Otherwise, molecule as such is neutral. Now remember, aromatic molecule like benzene, what type of reactions it undergoes? It undergoes substitution reactions. Therefore, if I take an activated benzene with large electron density being high, it undergoes electrophilic. If I take a benzene with a deactivated ring with a plus, deactivated means electrons are moving away from the ring, it encourages what type of reaction? Nucleophilic substitution. Suppose I take this molecule, suppose imagine I am adding an electrophile. This molecule responds, I get the electrophile substituted here. Suppose imagine I am adding nitron group here, NO2 plus, to azulene molecule. I realize this NO2 comes in the 5-membered ring, typical of benzene reaction, substitution reaction. On the contrary, If I take this molecule and imagine I'm adding a nucleophile to this, let us imagine a nucleophile. Take an example, NH2 minus nucleophile. In that case, it gets substituted in this seven-membered ring because the electrons have become depleted from that because the dipole moment creation. So this should actually summarize how the aromatic character can be thought of either in five-membered ring or seven-membered ring or three-membered ring or even eight-membered ring. Ultimately, a combination of five and seven-membered rings also. Hope this point is clear till this point. We shall stop now. Next class we shall take up those cyclic compounds which contain heteroatom, heterocyclic compounds like nitrogen, like phosphorus, like sulfur, like oxygen. That is for next session. Thank you very much.